Hello everyone. Today we will start with the stochastic part of stochastic models in finance. Of course, we have had some random variables earlier, but now we will go into core stochastic process mode for a few lectures. We will learn some theory and then we'll get back to the applications of this theory to models in finance. Okay. So, if you can recall, there are two things associated when you define a stochastic process. One is the time component, which is generally known as index set, and another is state space. Correct? So, depending on whether you have a discrete or continuous index set and a discrete or continuous state space, you can divide stochastic processes into four parts. So, here I have discrete time or index set and continuous index set. Similarly, for state space I can have discrete or continuous. Okay, so you know that discrete time, discrete state space lead to your usual Markov chains with which you started the stochastic process. What about the other sections here? So continuous time but discrete state space, examples that you have learned, for example, counting process or Poisson process, which actually is special case of counting process, then birth death process, all these come under this. So the state space is discrete because you are still counting events, but the time space is now continuous. Okay. Then continuous state space and discrete time. Can you think of some example here? Correct. All your usual time series data, whatever you did in time series analysis, all that comes under this because you had a Gaussian assumption for the values. So the state space was continuous and you had time interval as discrete. And continuous thing. So time is continuous, state is continuous. One of the common example of this is Brownian motion or Wiener process. So in this part, we are going to study Brownian motion. I'm sure you must have studied Brownian motion in the stochastic process course, but I'll still go through some basics which we would be needing here. Okay, so I'll be repeating a few basics which we'll need here. So Brownian motion actually comes from generalization of random walk. So let us first revise a few properties of random walk. So what is a random walk? So you have, say, a particle starting here, and this particle can move either to right or to left with certain probability, okay, and with certain time, after certain time. So random walk we are going to consider as, of course, discrete time, discrete state space. So we will say after each 1 unit of time, it units 1 unit in either right side or left side direction. Okay. So we basically have variables xi which denote the movement. So xi is either +1 or -1. +1 if the movement is in the right, on the right side, -1 if movement is on the left side. So +1, let us say with probability p, and -1 with probability 1 minus p. Okay. And if you take p equal to half, then it becomes symmetric random walk. In general, it is just a random walk, but if we take p equal to half, it becomes symmetric random walk. Okay, so this is xi, but xi is not random walk. The random walk process gives me position of the particle at time t. Okay, so whatever can give me position of the particle at time t, that process we are going to say is actually a random walk process. So position of the particle at time t. So I define, say, yt as sum over I going from 1 to t. We are assuming t to be discrete xi. Okay, why? Because the position would be decided by addition of all xi. So suppose x1 is minus 1, x2 is plus 1 and x3 is also plus 1. Then the final position is, so x1 is minus 1, so my y1 is here. Then y2 is position at second time point and it is plus 1. So the particle is moving in positive direction after y1. So it would become this. So this becomes my y2, addition of these two, and y3 becomes this. So y3 becomes just 1 if this was 0. Okay, if the particle started at 0. So we are going to assume that the particle starts at 0. That is y0 is 0. Then this definition holds. Okay. Okay, so this YT process is known as random walk, and we are not going to assume as of now any restrictions to the right or left side, so it can go on moving continuously for an infinite amount of time. Okay, so it's a random walk on just the real line, unbounded real line. Okay, there are no barriers on either end. By the way, this is random walk in one dimension. You can analogously define random walk in two dimension where up, down, right, left, 4 movements are possible. Similarly, you can go for random walk in 3 dimension where 6 movements would be possible, right, left along each coordinate axis and so on. And you have studied some properties of random walk in stochastic process, right? Persistence, and I mean the type of states, whether the states are persistent or transient, etc. So try to Google and see what happens to 2D and 3D random walk, and you will come up with an interesting quote, okay, to remember the properties of random walk. Okay, what happens to a drunk person, drunk bird, and then something like that. Okay, so do Google and let me know if you find that quote. Okay. Okay, so getting back, my YT is defined as this. Now, in time series, you have learned the concept of a stationary process. So, what's a stationary process? If joint distribution remains constant, so if you have, say, for marginal distribution, I will say distribution of y1 is same as distribution of y2, y3 and so on. Then binary also means y1, y2, y2, y3, in general any yj plus 1 should be same. Similarly yj plus 2, or if you take say k tuples, etc. So all these joint distributions, if they are same, then we say that the process is stationary. But in time series you also had something called as weakly stationary. So in weakly stationary you just check mean and variance if it exists, and if mean and variance is same, then you say that the process is weakly stationary. Okay. So what about random walk process? Is it stationary, either strong or weakly? So let us check. So if I want to compute expectation of yt, I am going to need expectation of individual xi's, correct? So what is the expectation of individual xi? Now it depends. So if I consider symmetric random walk, then it is going to be something. If I consider non-symmetric random walk, then it may be different. So in general, expectation of xi would be p into 1 plus 1 minus p into minus 1. So this becomes p minus 1 plus p. So it is 2p minus 1, correct? 2p minus 1 is expectation. So if in particular I have a symmetric random walk, then p is half, so this expectation becomes 0. Okay, so in general expectation of yt is 2p minus 1. Of course 2p minus 1 into t, because you have sum over I going from 1 to t. So this expectation is dependent on t if p is not equal to half. Okay, so But if p is equal to half, then expectation of yt is 0. Okay, so at least the mean remains constant if p is equal to half. What about variance? What happens to variance? Now when you define random walk, you assume that your xi's are IID. Okay, so the distribution of each xi is same and they are independent. So when I want to compute variance of yt, I would just have to add variances of individual xi's. Okay, so what can I say about variance of individual xi? So variance of xi we know is expected xi square minus expected xi whole square. Now we also know expectation of xi square. Xi square is going to be either plus 1 or plus 1. Basically both xi's are 1 in magnitude. So xi square is always going to be plus 1 and hence expectation of xi square is just 1 minus mean is 2p minus 1 whole square. Okay, so this is 1 minus 4p square minus 4p plus 1. Okay, 1 minus this, so it becomes 1 would get cancelled and I am left with 4p minus 4p square, so 4p into 1 minus p. Okay, 4p into 1 minus p, so if p is equal to half, it becomes 1. So variance of yt is t times 4p into 1 minus p. So if p is equal to half, variance of yt is t. Okay. So variance of yt is t means variance is not free from t and hence we would conclude that the process is not stationary. Okay. Therefore, random walk is not a stationary process. This is important. Okay. Now, so I have computed mean and variance of a random walk and I have proved that it's not a stationary process. But we know it has some other properties. So one of them is the stationarity and independence of the increments. Okay. So stationarity and independence of increments. What is meant by an increment? So increment would be what happens when you progress in time. So after certain units of time, what happens? So whatever happened between that interval, so ys minus yt would become an increment if s is greater than t. That is necessary. Okay. So what do I mean by stationarity and independence of increments? Okay, so ys minus yt, if I want to consider, how do I write it? By definition, ys is sum over I going from 1 to s xi and yt is sum over I going from 1 to t xi. Okay, so this becomes sum over I going from s plus 1 to t xi, correct? Now, what it means, it is because xi's are identically distributed, the distribution of ys minus yt depends on just how many xi's are involved here, correct? So, y3 minus y1 will have same distribution as y4 minus y2 or for that matter y100 minus y98 because each of these would involve only the distribution of two xi's. So basically say x1 plus x2 because they are IID. Okay. So that's why my increments have stationary distribution. So the distribution of the increment depends only on the lag s minus t. The number of lags involved is s minus t and the distribution depends on only the distribution of these s minus t xi's. Okay. So they are stationary, and they are independent because again exercise are IID. So when we say increments are independent, we have to talk about non-overlapping increments. Okay. Even this is fine because it's open on both sides. So having a common endpoint is fine. It's an open interval. So whenever you have non-overlapping increments, the exercise involved in both would be completely different. And since exercises are independent, the increments have independent distribution. Okay, we have seen this in probability theory that continuous functions of independent random variables are independent. Okay, or Borel functions to be more precise. Okay, hence the random walk has stationary and independent increments. Okay, now we are going to study a few more properties of random walk. So one of them is what is known as quadratic variation. Okay, so what is a quadratic variation? As the name suggests, it is some sort of it is trying to capture some sort of variation. Now given a stochastic process, you can observe only one realization of a stochastic process. Let me try to explain what I am saying. See, for example, when you have recorded say data on rainfall at Pune city, daily rainfall. Suppose today's rainfall was 3 millimeter. But we know that 3 millimeter is just one possible value. It could have very well been 2 millimeter or it could have very well been 5 millimeter. Those values also had some chances of occurring. Okay. But because we observe every event only once, we don't get to see multiple realizations of today's rainfall, and that happens for the entire process. So whenever you have processes which are progressing in time, you always get to see only one realization of that process. And we know in usual theory that whenever you want to compute variance of something, you need multiple realizations. However, in stochastic process, we don't have that luxury. In fact, that's why in time series you need stationarity, so that estimation becomes possible. Otherwise, on the basis of just one realization, you cannot really do estimation and talk about its properties. Okay, so stationarity kind of tells you that okay, you can take every value as coming from same distribution and try to estimate mean variance. If not same distribution, at least you can assume every value to have same mean and same variance, weak stationarity, so that all of them can be used for estimation purpose. Okay, so in general, when you have only one realization, you cannot give a good idea about variance. In fact, you cannot get any idea about the variance unless and until you make some assumptions about the distributional theory. Hence, people came up with a solution. So, quadratic variation is one way of getting some idea about variance of the process. So, quadratic variation till time t is defined as sum over yi minus 1, where I goes from 1 to capital T. So basically we take difference between the two consecutive occurrences of that process, the two consecutive realized values of that process, and then we go on summing over that difference, and that is called as quadratic variation. Square. Of course, the word quadratic should tell me that there should be a square involved. So basically we are saying that how much deviation is there. So I have started a process here, and suppose my process goes something like this. Okay, this is general process, this is not a random walk. So in each unit of time, I am considering discrete time process. So in each unit of time, how much I have moved. So first unit of time, I have moved from here to here, means this much is the variation. So I take square of that. In next, I have moved from here to here. So this much is the variation. So I take square of that. And we go on adding. Okay. So this kind of tells me how much movement has been there, and that would help me distinguish between say these two processes. So this process has less variation, whereas this process has more variation. Okay, so we are trying to capture that using quadratic variation, because quadratic variation for this second process would be higher. Okay, because say this to this movement is there. And of course you need square because you don't want to cancel out the movements. Otherwise this and this, so these movements would cancel each other and we don't want that. Okay. So let me try to repeat. Quadratic variation is a quantity which can give us some idea about the variance of the process on the basis of just one realization. See, I am just using the observed data yi and yi minus 1. Whereas when I computed the variance, I did use the theory that I know about individual random variables. So for computing variance, you have to have some distributional assumption, some theoretical assumption. Whereas for computing quadratic variation, you don't need any theoretical assumption. Okay, that is one major difference between quadratic variation and variance. Second thing, what does variance do? Variance kind of considers all possible realizations, and then so variance of y3 would mean what are the possible values of y3 under different realizations. Take those values and then compute variance over them. But because this is not possible in real life, because you don't have multiple realization, quadratic variation cannot do that. Quadratic variation takes every realization and computes the value. As a result, quadratic variation is specific to a realization. So if a realization changes, it may change. Okay. So here it may be something, here it may be something else, and so on. Whereas variance takes care of all possible realizations. Variance talks about probability distribution of random variables coming under all possible realizations. Hence, variance is a constant quantity. Variance does not change from realization to realization, whereas quadratic variation is specific to every realization. Okay. However, in case of symmetric random walk, something interesting happens. What happens? So in case of symmetric random walk, in general in any random walk, yi minus 1 is going to be xi. So I get xi square I going from 1 to 2 as my quadratic variation. And xi square we know is always 1. So my quadratic variation till time point t would always be t for any random walk. Okay. And we know for symmetric random walk, this is also same as variance of yt. Okay, for other random walks, they are not same. For other random walks, variance was different. It involved p into 1 minus p also. So for other random walks, it is different. But for symmetric random walk, quadratic variation and a variance turn out to be the same. So this is an interesting property. By the way, another notation for quadratic variance is this inner product type of notation. Okay. So this is just other notation for quadratic variation. So random walk has unit quadratic variation at every step. So random walk collects one unit of quadratic variation for every unit of time. And in symmetric random walk, even variance is collected at the same rate. Variance increases at the same rate, 1 unit per unit of time. Okay. So this is an important thing. Let us stop here. We are going to study a couple more properties of random walk, but we need a few more concepts for that. So we'll get back to random walk when we study those concepts. Okay. Let me stop here. Thank you.